All right, today I want to show you a new ML model approach that's been a really hot topic of discussion on Twitter and other places. And that is the Kolmogorov-Arnold networks as an alternative to a neural net. So the motivation here was the idea that a neural net has a fixed activation function on the nodes of your graph, and this the Kolmogorov-Arnold network takes a different approach where they have a machine learnable function on the edge of your graph. And that machine learnable function is represented by some splines, and then they're simply added at the nodes. So where the neural network tries to take a multivariate input and map it to an output, one of the ideas in these cans is a theory that you can represent a multivariate function as a sum of univariate functions, that is one variable, and that turns the model into something where you're learning these functions that get added together. That's the theory. I don't want to spend a lot of time on that. Today I just wanted to see how easy is it to use, and what can we do with it. And so I wanted to do something with Lennard Jones. This is a 100-year-old atomistic potential now. It's pretty simple. It looks like here 1 over r to the 12th minus 1 over r to the 6th. So it has some nonlinearity, and we're going to look at making a CAN model for this data. All right, so CAN is built on top of Torch. We import Torch. I'm going to create a data set using their data set function. We have a Lennard-Jones function of one variable r. Here we return 1 over r to the 12th minus 1 over r to the 6th. And then I make a data set here. We look at this particular range because it has the nonlinearity and the minimum that we're interested in. And so here we make a data set, and here I plot the data set. And so this is the data we're looking to fit with the CAN. Okay, so let's just run it. I'll run it live so you can get a sense for how long these things take. So the first thing to do is make a model, and I'm going to start with the smallest model, maybe second to smallest, where we have one input, just two functions, and one output. And so we just make this, and then here we use LBFGS as the optimizer. We give it the data set, we call the train function. We'll just take 20 steps, and there's this cool feature called plot where it will show you what your model looks like. And so here's the idea. You can see one of the functions that we learn already looks like Lennard-Jones, and then there's this other piece over here. And it probably takes some practice learning how to interpret what all of these are, but these things end up getting summed into the answer. And so if we look at what happens here in the fit, so we'll make a fit space here that just is from min to max of our input. And then we can simply evaluate here. We evaluate our model, so it's really nice syntactically. You just call it like it's a function, and because it's in Torch, we just detach it to get an array for plotting. And you can see with just those two functions, really, nice that it fits. Maybe this is something because of splines, that there's some illusion of how good this fit is in general, but it's pretty straightforward and it looks really nice for not that much effort. This is even easier in my experience than fitting these with neural nets. Neural nets are kind of, they can be a little bit tricky. You certainly probably couldn't fit this with 2 neurons. You would need many more neurons, and then because of random initializations, you probably have to run it a few times before you get something pretty good. Now, when I talk about neural nets in courses I teach, I always ask, what happens when we extrapolate? So we have this idea that we've found functions that add up here, but what happens when we get out into the data space outside? And what I'll show you here is cans do not save us from that. So if I pick a broader range here, let's say 0.7 to 5, you can see down here that weird stuff happens. So we definitely did not learn the Lennard-Jones function in training this data. You see something unusual here. This should be going up to infinity, very repulsive, and you see that it doesn't. In fact, it's going to turn back down. And it's even interesting. Let's look at a even broader window. You see it's going down here. Let's do -10. That doesn't mean anything in distance space. You can't have a negative distance, but it's still curious to see like what is actually happening, and can we figure out. So here it looks like it's going to some constant, and if I do it on the other side, it looks like it does something that looks approximately linear, almost looks like some kind of like long-range ReLU form. I don't know if that is reasonable. In neural nets, we know that activation functions determine the long-range extrapolation behavior, and it's just actually not obvious what controls that here. It might be if you study the network and how the spline works. Eventually, splines must be extrapolating and going off. Maybe it's constant or something different. But as cool as the can is, it doesn't save us from this extrapolation issue. So it's still pretty early days for them. I think they're really interesting, and they might have some applications in places. Like I said, it's pretty amazing we can fit with just the 2 neurons in this case. But there's a lot of things we don't know, like what happens when there's noise. Does it readily overfit? Are there regularization strategies? Are there ways to control the extrapolation behavior? Like if you want a particular behavior, can you build that in? Uncertainty quantification, I think, is a big one. You know, with neural nets, there's probably a dozen approaches: dropout, Bayesian approaches, ensembles, bootstrapping, etc. Maybe there's a way to do that with cans. Who knows? These are just out like less than a few weeks, and neural nets have been out for some decades. So there's a lot of reasons why you might still want to use a neural network for anything along those lines. But the cans are pretty interesting, and it'll be fun to see how they evolve. There was a note from the author in the GitHub repo about efficiency and scaling. It's too early to wonder how do you scale a can to a billion somethings. Those days are coming, and otherwise it'll just be really interesting to see how this evolves, and so I thought it'd be fun to make a little video about it, and so now you have it. Thanks for coming.